My name is Munagala Ramanath. I'm a software engineer and an Apache Apex committer. Today I'll be talking to you about Apache Apex, which is the leading streaming platform for distributed applications. Apex is, before we get into the details of the talk, let me draw your attention to an announcement. We have our Big Data World Conference that's currently ongoing in Pune, India, February 10th, 2017, and there will be one April 4th in San Jose, California as well. So if you happen to be in any of those towns, feel free to come by. Apex is, as I mentioned, a streaming platform. It's open source, it's probably worthwhile spending a minute or two talking about what a streaming platform really is, because sometimes people come in with various questions about that basic item. So streaming platforms allow you to write distributed applications. Distributed applications are applications that run on a cluster of machines, not just on a single machine. And on each machine of the cluster, you have a part of the application running, a process, in our case, a Java JVM process. And these different components process data that comes into them and output the results of their computation to downstream components of the application. So these applications typically tend to be more difficult to write because you're essentially programming multiple computers to behave in a coordinated way. In the sphere of distributed applications, we can distinguish between batch operations and stream operations. So applications that typically process batch data are somewhat simpler to write because batch data has a well-defined beginning and a well-defined end. So the data stream for batch, for example, might be a set of files that are already present in a directory, or it might be a set of records in a database, something like that. Whereas streaming data has no beginning and no end. It's unbounded data. So what's examples of streaming data? Well, a couple of common ones are the following. One is data coming in from the Internet of Things, sometimes abbreviated as IoT. A specific example of that could be a power company that has a windmill farm. It might typically have hundreds of windmills. Each windmill has a couple of hundred sensors on it, and these sensors are constantly emitting data about the part of the windmill that they're monitoring. It could be wind speed, it could be the speed at which the rotor is turning, it could be the angle of the rotor. Numerous factors are monitored. And this data is constantly coming into a server someplace, and it never stops because the windmills are out there spinning 24/7. So the data then needs to be analyzed to see if any of these windmills are operating out of spec, and if so, it might be an indication that some parts are wearing out and they're due for replacement or repair, and a crew needs to get out there pretty soon. So those sorts of decisions need to be made on the streaming data. We can't wait for the data to land someplace and then process it all in one go. Another example is a clickstream for a popular website. So people around the world will be visiting that website and clicking on various parts of it 24/7, 365 days a year, and those clicks need to be processed. So that's the environment for which Apache Apex was designed. We also process batch data because batch data is inherently simpler to deal with. It can be considered a special case of streaming data that has a well-defined beginning and a well-defined end. The Apex platform consists of two components: the core platform itself and a library called Malhar. So typically a distributed application like this will need to interact with a variety of external systems, such as message buses, databases, file systems, and so forth. Our Malhar library gives you pre-built connectors that can connect to all of these endpoints and either pull data from those sources or write the results back out into those sinks. Okay, so we'll look at, for the purposes of today's talk, at a prototypical application that's illustrated by the diagram near the bottom of the screen. It shows a browser interacting with a web server. That was the second example, roughly speaking, that I gave you, except in this case, the web server is outputting log data. So the data stream that's being processed by this application is a series of log messages that will be written to Kafka. Kafka is a message broker, distributed message broker. And the log messages then will be pulled from Kafka by the Apex application. The Apex application in this instance consists of three pieces. One is the input piece that pulls data from Kafka, the log messages. The second is the computational piece, which parses the log messages. It might have to decompress them if they're already compressed, parse them, filter out the messages that are not interesting, and pass those on to an aggregator that computes various dimensions and aggregations as to how many messages are coming out per second, per minute, per day, whatever, and write the results out back out to Kafka. So even though this example shows input coming from Kafka and going out to Kafka, those two endpoints, as I mentioned before, can be anything else as well, like databases or file systems or object stores, things like that. So, okay, so we'll discuss additional pieces of this application as we go along through today's presentation. All right, so Apex from the beginning was designed to be very fast, high throughput, low latencies. Because the whole focus is processing the data in memory as far as possible. So if you have a cluster that's well provisioned with lots of CPUs and lots of memory, then there's very little data that needs to go to disk while the application is being processed. There are applications that don't need to go to disk at all, and those we call stateless. There are other applications where if the operators are maintaining some sort of state that needs to be preserved over time, then that state will periodically get written to disk. But it's a very small amount of data that's written to disk very infrequently. And because the bulk of the data processing happens in memory, it is very, very fast. There are no artificial latencies introduced into the system. Now, in the previous example that I was talking about, we mentioned these three components: the unit that pulls data from Kafka, the unit that parses, and the unit that does the aggregations. These components, we call them operators. So you can think of an operator as being a standalone Java program that has certain input ports and certain output ports. It receives data on its input ports, processes them, and emits results on its output port. And this operator can run on any node in the cluster. Apex applications are designed to be fault tolerant and scalable right from the start. So the programmer himself does not have to do anything special to take advantage of the fault tolerance. The platform itself monitors all these operators, and if one of your operators, for example, runs into a problem of some sort, maybe it gets a null pointer exception or some sort of unexpected exception and dies, the system will monitor that and then restart that operator without loss of data, and the application will continue processing. The application, for example, could die because the node on which it was running experienced some sort of a hardware fault, and the node itself failed. Again, the system, in conjunction with the lower layer of Hadoop and Yarn, will detect this, and the operator will be restarted on some other node in the cluster, and without loss of data, the application will continue processing. We have, looks like, one question, and the question is this presentation going to be available later? And the answer is yes. It is being recorded, and you folks will all get the links to the slide deck as well as the recording. Okay, so the programming model, as I mentioned, these are Java applications. The model is very simple, a very simple Java API to express your business logic. And that's really all you need to worry about in an operator. So an operator, briefly put, is just a Java class that implements the operator interface. Now, as part of that interface, there are a number of callback functions. So the way you would write your code is you would write functions for those callbacks and put your logic in there. There's no main program for you to write. The main program is within the platform logic. And these callback functions typically are of two kinds. One is the lifecycle callbacks. So when an operator starts up, there's a callback that a sort of an initialize function. Setup is the name of the function. And in that setup function, you can do whatever you need to do to initialize the fields of the operator. Similarly, to match the setup, there's a teardown. In case your application terminates, then you can wrap up things like closing down connections to databases and things like that in the teardown function. So that's one category of callbacks. The second category of callbacks is functions on these input ports. Operators, recall that I mentioned that they have input ports on which input data comes in. These units of data that come in, we call them tuples. You can think of them as records. So when a record comes in, a method on the input port called process will be invoked with that tuple as an argument. And you can do whatever you want with that data unit that comes in. And typically one of the things that you would want to do is to output either that same record or a modified version of that record on one or more of the output ports. So the output ports themselves will also have a callback function called emit. And you would invoke that emit function with the results of your computation. So the model is very, very simple and lets you express your logic in a clear and straightforward way. Okay, looks like we have another question, and that is okay, so it says operator fault tolerance. Is there a pre-configured default behavior? Is it possible to override that behavior? So fault tolerance itself is, and I believe, not overridable, because if an operator fails, you would typically want to restart it and keep the application going. So is there a pre-configured default behavior? Well, the default behavior is to restart the operator and restore its state. So the state, what is the state for an operator? Well, it's a two-part answer. So one part says that your operator can be written in such a way, if your application is of that kind, in such a way that it has no state at all. And if it falls into that category, then you can annotate the operator with a Java annotation saying @stateless. And in that case, no state information will be saved to disk, so it will go even faster. The other kind of operators are those that have state, and state just means fields in your class that maintain things like counts. So take a very simple example. If you're counting the number of incoming tuples, that variable, that integer variable, is part of state. And if the operator goes down, you would want to save that state, and when it comes back up, you want to restore that count and continue counting from that point on. So that is the default behavior. As far as overriding parts of it, the state itself is currently saved to HDFS, and you can override where it's saved to, because we have an API that defines what the storage system should be doing. And you can, if you have your own storage system, you can write classes that support that API and then save it to that system. And in fact, within Apex, we have support for a distributed in-memory key value store called Geode. So Geode is also open source. You can look it up. So instead of going to HDFS, if you want to go to Geode, that's also a possibility. So various parts of that behavior can certainly be overridden. Another question is, how does Beam and Spark and other things compare to Apex? I don't want to get too far afield in comparing Apex with other systems, but briefly said, Beam is actually a layer on top of streaming systems that supports multiple streaming systems. And one of the components of Beam is a runner, the core system, the core streaming system that actually runs your pipeline, your application. And Beam already supports Apex, so you can run Apex applications within Beam by using the Apex runner. As far as Spark is concerned, Spark is a micro-batch system, so it's actually inherently a batch system that's been adapted to streaming data. So there's some significant latency, artificial latency introduced because of that batching. In every operator, you have to wait until the entire batch is available before you can start processing. In our case, as soon as a tuple comes in, you can process it and send the output right out. So Apex will typically, of course, it will vary depending on your application, but very often we find that Apex has significantly lower latencies than Spark. I have another question here that says, what is the data format of tuples? Can I send over a tuple of any format? And the answer is yes, you can send over a tuple in any form. You have to define a Java class that holds it, because everything ultimately is Java. So if you define your class to hold all the fields that your tuple is going to have, then our operators are all written using Java generics. So you would instantiate the operator with the generic type to be the type of the class that you just created. So there are no size limits on the size of a tuple or the type of a tuple. Hopefully that answers the question. Okay, let's move on. I mentioned scalability. High throughput and low latency we've already talked about. Scalability just means being able to handle huge volumes without skipping a beat. And the way we do that is by what's called partitioning. And partitioning really, what it means is replication of operators. Think about it in concrete terms as, let's say you're chopping some vegetables and you have one person chopping the vegetables. Well, he's going to have a certain amount of throughput. If you wanted to speed it up, if you had 10 other people who could chop that same set of vegetables, you'd go 10 times faster. And there what you've done is replicated that one person 10 times. Using that analogy, it's an almost exact fit, because every operator in an Apex application can be replicated any number of times. For your data stream, you can decide that, let's say your input operator that reads from Kafka needs to be replicated 8 times. You will then have 8 copies of that operator running in your cluster, and they could all be running on different nodes. So you get near linear speed up. So that's what scalability is. So deciding beforehand that you need 8 copies of that operator is an example of what's called static scaling or static partitioning. We also use the term partitioning for this replication. Our platform, Apex, also supports dynamic scaling, meaning at runtime, the operator can decide that the volume of data is getting to be so large that it's experiencing very high latencies or low throughput, and at that point split itself or replicate itself into multiple operators to increase the throughput and reduce latency. So our platform, I think, is one of the very few that supports dynamic partitioning. We already covered fault tolerance and correctness. Because of the platform's inherent ability to save state and restore failed operators without losing data, you have essentially correctness. The saving of state, periodic saving of state, is called checkpointing, and that's, as I mentioned before, done to HDFS. The semantics by default are what's called at least once. So every tuple is guaranteed to be processed at least once throughout the pipeline. So if an operator fails and the tuple did not get processed by that operator, well, when it comes back up, it will be resent by the upstream operators and it will be processed. So at least once. Why do we say at least once? Because the recovery happens at the checkpointed states. So let's say you have a checkpoint and then a few tuples were processed and the operator went down. It will be restored to the previous checkpoint. So the few tuples that it already processed in the previous run will be reprocessed by the operator. So it could end up in failure scenarios processing some tuples more than once. So exactly once is achievable if your operators are what's called idempotent. Idempotent means given the same input, they generate the same output. So even if the operator ends up reprocessing some of those tuples, if you get the same results coming out, your application behaves as if it had exactly once semantics. And in a distributed system, that's really the best we can hope to achieve. Operability, we offer commercial components around Apex, which allows you to monitor the whole system as well as all running applications and operators using a browser console. So operability is a standard part of our proprietary offering. Okay, so moving on, here we see the way Apex is layered. As I mentioned before, Apex depends on Hadoop. Hadoop is an open source project that has two parts to it. One is the HDFS distributed file system, and the other is Yarn, which is a resource manager. So on top of that, the core platform works with Yarn to request resources when an application comes in. If an application comes in and it has, let's say, 5 operators, then the platform will request 5 containers from Yarn. Yarn knows about all the nodes in the cluster. It will respond by providing the 5 containers with the appropriate CPU and memory resources. And the platform then will deploy the application on the cluster. Layered on top of that, we have the Malhar operator library that has many different categories of operators already pre-built and ready to go. We'll see some more details of those categories in the upcoming slides. There's also a high-level API that saves you some of the routine parts of Java coding. It abstracts it away. And as I said before, batch processing is also supported by the platform as a special case of streaming. We also have a set of application templates which can be downloaded from either our website or directly from our RTS system. And these templates further simplify the process of writing Apex applications because they're already pre-built applications that are ready to go, and in most cases what they do by default is transfer data from some predefined source to some predefined sink. So for example, we have templates for reading from Kafka, writing to HDFS, or reading from HDFS, writing to HDFS, or reading from JDBC, writing to HDFS. So many of these combinations are available and more are being added. So the source code for these application templates is also available, so you can just download the source code, and if it approximately fits your use case, you can then add whatever custom code you want to finish the application. The commercial offering that I mentioned, which is called RTS, has a management and monitoring console that's browser-based, a very rich user interface. It allows you to also do real-time data visualization of the data coming out of any operator, for example. And there's also a piece that lets you do drag and drop application assembly. Okay, so looks like there's one more question here. Okay, so it says, the question says, is there any way to handle the tuple dependencies without impacting latency? Say the result of one tuple is sent to process another tuple. Not sure I understand the question. Maybe if you can elaborate what you mean by it. If you can provide a bit more detail on what exactly you mean by that, I can answer it. Right now, I don't quite follow the question. Okay, let's move on. Here's another representation of the this is a general DAG, actually. The operators of an application are connected together to form a directed acyclic graph. So that's sometimes abbreviated as a DAG. So you cannot have any cycles. So in this case, the first operator is sending tuples to the second operator, which then does presumably some filtering, writes some of them out to the next operator on top, some of them out to the next operator on the bottom, and then those two come together in yet another operator, and then finally get written out to the output stream. The tuples that are written that travel from the output port of an upstream operator to the downstream input port is called a stream. And when you build an application, you'll typically be doing 3 steps once the operators themselves are ready. Okay, that's a preliminary step. Let's assume that's done. So once the operators are ready to build the application, what you'll be doing is creating instances of those operators and then configuring those operators by setting some properties. And then the third piece is creating the streams that connect one operator to the next. Okay, so we'll see examples of that as well as we move on. A typical operator takes one or more input streams, performs computations, and emits one or more output streams, as we mentioned before. I mentioned partitioning, and that's also being illustrated in this diagram here because each of these blue rectangles are actually stacked up 3 deep. So that's meant to illustrate the fact that the operator can have many replicas that share the load of processing the input stream. All right. So here's a diagram that shows how a Apex application fits into the cluster running Hadoop. So here we have 4 nodes in the cluster in this illustration. You have a box with this dotted boundary on top that says Resource Manager. That's Yarn. And Yarn is in contact with all the nodes of the cluster because it has to know how many resources of each kind are actually present in the cluster. The NM stands for Node Manager, which is a daemon that runs on each node. The different colors are meant to illustrate the fact that Apex is a good citizen on a Hadoop cluster. It does not monopolize the Hadoop cluster. It can live with other applications that are running at the same time on the cluster. So you don't need to dedicate the cluster to Apex. You can have MapReduce jobs running at the same time, and those are shown here in pink, running at the same time as an Apex application that's shown in green. So you see this green box here that says STRAM. Now, any application running on Hadoop needs to have what's called an application master. And in our case, we call it STRAM, which is short for Streaming Application Master. So the application master orchestrates and monitors the other operators that are part of this application. So this application has 1, 2, 3, 4, 5, 6 operators. Now notice that multiple operators can be deployed on the same node. They can even be deployed within the same JVM container as well. So you have control over that. The green dotted arrows show the data flowing from 1 to 3, and then 3 to 4, and then 4 to 6, presumably, and possibly also 3 to 5, in all sorts of ways. As long as that graph has no cycles, you're okay. Now, connecting to the resource manager is what's called the gateway and the DataTorrent console. That's our proprietary offering. And there's also an Apex CLI, which is the command line interface. That's part of the open source Apex project. You can use that command line tool to launch applications as well as monitor applications. Okay, so here's a diagram that illustrates some of the details of a word counting application. Let's say it pulls from Kafka. You have an operator that reads the input. You have a parser. And then you have a filter that gets rid of unwanted words, and then a word counter. And then finally, the frequencies of words are written to a database. So, oops. This essentially shows you the steps that I mentioned before of creating an application. So you develop your operators first, then you connect them to form the application, you configure them. The configuration, by the way, can be done either in Java or using an external XML file. Either way works. You then specify certain scalability properties if you want. You then can test and then iterate based on your performance needs. Okay, so here's the categories of operators that I mentioned before that are available. So relational databases, we have connectors to Vertica, MySQL, Oracle, JDBC, file systems, HDFS, Hive, NFS, S3, NoSQL databases like Cassandra, HBase, MongoDB, Aerospike, and so on. So there's many of these connectors to external systems that are already available and ready to go. There's a lot of documentation available at docs.datatorrent.com. I'll show you very quickly the website towards the end of the presentation. There's also a number of example applications available on GitHub that you can also take a look at. They're available with full source code, so you can look at the source code and adapt it for your own needs as you see fit. We go through an internal process of certifying operators to make sure that they're production ready. We also do some benchmarking as well. Okay, so here's an example of a filter operator. It extends base operator. Base operator is provided, but it doesn't do very much. All the required methods in the interface are empty methods, so that you don't have to define methods that you don't need to. And what it does is it receives input that's English words. It examines the words, and if they happen to be articles, English articles like a, an, or the, it will throw them out. But if it's any other word, it will emit that word on the output port. So at the end of the class, you'll see there's the output port, just called output. It's just a Java field. And notice that it's annotated with transient. So any fields in your class that you don't want saved to disk as part of the checkpointing, as part of the state of the operator, you should mark it using the Java keyword transient. So that will make your application go faster because there's less operator state that needs to be saved as part of the checkpointing process. Similarly, we have a input port, and the input port is defined directly here as an anonymous class overriding a single process function that I mentioned before. So the process function will be invoked by the platform whenever an input tuple comes in. So a tuple in this case is just a string. So it gets a word as a string, and then it invokes the contains method on the article set to see if the incoming string is part of that set. If it's not part of the set, then it emits it on the output port. If it is part of the set, then the function does nothing and simply returns. Okay, you can see from this how simple it is to write an operator. Okay, here's an example of once the operators are all ready, connecting them to form the DAG as the final step of building the application. So the class itself, you can call it anything you like. In this case, it's just called application. It's annotated with this name. And this is the name that will be shown on the user interface when the application is running. The only requirement is that it should implement the streaming application interface. And that interface has only a single method in it. It's called populate DAG. So that method takes two parameters, a DAG and a configuration. In this case, I believe the configuration is not used. But if there's something in there, there's occasions when you might need something from there, so it's passed in as a parameter, but in most cases you won't need to use it. So here we create the operators, the Kafka input operator, the parser operator, the filter operator, the counter operator, and finally the output operator. They're all created by invoking the add operator method and giving it a string as the name for this instance, and as a second parameter passing in the class object that you want to instantiate. So the system will instantiate an instance of that class and return that object to you as the result of the function call. So once you're done with that phase of operator creation, you then have to go to creating the connections or the streams. So here we see the output port of the Kafka input is connected to the input port of the parser. The output port of the parser, in turn, is connected to the input port of the filter, and so forth. And the first argument, as with operators, is just a name for the stream. So that quoted string there that says lines, words, filtered, counts can be any string you want. It's just a name that the system will use to refer to that stream. Okay, so that gives you a capsule idea of what it takes to build an Apex application. All right, so we mentioned partitioning. So there are some subtleties involved in partitioning, because if you have a single operator that's, say, computing counts, then if you split that operator into, say, 3 replicas, each replica then is only going to have a partial count. So somewhere down the line, those counts have to be added together to form a final count. So that's the role of a unifier. So a unifier is a special type of operator that the system will insert for you if you don't specify it. But if you have some custom logic for performing that unification, that will take the data coming in from all the partitions of an operator and then combine it, you can write your own unifier as well. So that's also customizable. But once partitioning comes into play, you need to have a unifier downstream of it. So here we have operator 1 being 3-way partitioned, and it has a couple of unifiers. Operator 2 is partitioned 2-way, and that also has a unifier downstream of it. The second diagram illustrates a different topology. So this kind of partitioning, shown before in the upper diagram, can cause tuples and their results to be shuffled. If you want to avoid that shuffling, then you can say that you want what's called parallel partitioning. And what that does is an entire linear sequence will be replicated in its entirety. So a tuple reaching 1A will not go to any of the B operators. It will stay in that linear segment, go to 2A and 3A, and finally to the unifier. So in some computations, some applications, this is more appropriate. So that's also available. Now, when you have a large number of partitions, I mean, it's not unusual to see 100 or 150 or 200 partitions when you have a large data stream in a large cluster. The unifier itself can potentially become a bottleneck because it's receiving data from 200 upstream operators. So in that case, you can split the unifier itself into a cascading pattern that we call a cascading unifier. And that's illustrated in this third diagram here. So you can say each container should get input from no more than 2 operators. So what it will do is if there's 4 upstream operators, it will create 2 operators, 2 unifiers to receive that data. And then the results of those 2 unifiers will go into a third unifier. So that load, that computational load, is spread across more unifiers. Now, the disadvantage is that these tuples then have to traverse your network interface cards on multiple nodes, which can cause additional latencies. Okay, so dynamic scaling is the next topic. Before we touch on that, looks like there's another question. Okay. Okay, let me read this question here. How is Apex going to handle events which keep coming up while processing of existing events takes some time? In an online game, events keep coming across. A few of the user events are being processed by Apex operators, and a few user events come up in between. How will Apex handle those? Is there a sliding window concept? Yes, we do support sliding windows, but I don't think you really need the notion of sliding windows in this case. This is just asking about high volumes of data that flow in while the previous data is being processed. The answer is the inherent nature of the DAG architecture will automatically handle that, assuming that your cluster has resources. So in this diagram, the first diagram, for example, let's say input events are coming into operator 1. So your first cut at an application can have some computational logic inside that one operator. As you find higher and higher volumes coming in, you realize that this operator, the first operator, is doing too much work. So then what you would do is split the work that it does into just the ingestion part, where it receives the data coming in from the outside, does some very, very minimal processing, and then offload the rest of the processing into operator 2. So this is a usage pattern, a coding pattern that is a sort of a best practice for writing Apex applications. Don't try to do too much in one operator, because then that operator can become a bottleneck. Instead, if you spread that work into, say, 2 or 3 pieces, sequential pieces, you can then move each piece into a downstream operator, so that the downstream operators, 2 and 3 in this example, can continue processing while one continues to receive input. Now, one of the later slides will talk about an internal component of Apex called a buffer server, which actually will buffer the tuples in each operator. So, for example, if operator 2 happens to go down, there's a buffer server in 1 that has a lot of those tuples in memory, and those tuples will be replayed. So these buffer servers themselves also help to buffer up the data in case the downstream operators are not able to handle the load. So Apex has a number of different knobs to turn, configuration aspects that allow you to handle very large and very heavy loads coming in. All right, so here, this shows you about dynamic scaling. So as you're running with operators 1 and 2 partitioned into 2 replicas, you might realize, operator 2 might realize that the load is getting to be too much, and the throughput is starting to decline, at which point it can partition itself into 4 copies. So now the load is spread across 4 operators, and move on. So you still keep up with the flow, assuming that your cluster has the required resources. The opposite can also happen. As the input flow ratchets down, perhaps at nighttime, when fewer users are doing something with on the input side, for example, as the flow comes down, these operators can then be collapsed together into a smaller number. So you can either scale up or scale down based on the input load. Okay, so this partitioning logic itself is also customizable. So we have a well-defined API for that. So you can either use the predefined logic, the predefined partitioners, or you can write your own where you decide based on the particular aspects of your data and your application when you want to partition the operators and how many replicas you want. So that's completely customizable. Okay, so this shows you an example of the runtime topology when partitioning is in effect. So here's the unifier, and we have parallel partitioning here. Okay, I'm going to skip over this slide because it's just illustrating the notion of a window. We have time-based windows that are by default half a second, and you have callback functions called begin window and end window that will come into your operator that get invoked. And you can put whatever logic you want inside those functions. If you, for example, have nothing to do when a new time window starts, you don't even have to implement that begin window, but it's there if you want to override it. Okay, so here's the buffer server that I mentioned. there's the Java JVM container in node 1. The buffer server buffers the output tuples going out of the operator 1. And if operator 2 happens to go down, it will resend those tuples from the previous checkpoint. When the entire DAG has finished processing a set of tuples, the buffer server then will get rid of it from its memory. So the cleanup happens automatically, because the entire state of the DAG is made available to every operator. Okay, exactly once, I mentioned this briefly before, you have at least once is provided by the platform. Consistent state is also provided by the platform. Item potency is something that you have to be careful about and mindful of when you're writing your own operators. Item potency, as I mentioned before, just means that if the operator is presented with the same input, it should generate the same output. That's generally not very hard to achieve. Now, if you want to also ensure that duplicate data is not written to the sink, then additional care is needed in the output operators. So, for example, in our file output operator, we store the file offsets associated with each checkpoint. So let's say certain tuples have been written to a file, and then the operator goes down. It will come back up and be restored to the previous checkpoint, and the records from that old checkpoint will be reprocessed by the operator. So if it writes to the same file, you'll end up getting duplicate records. So in order to avoid that, our file output operator will actually keep track of the offsets in that file for each tuple. So when it comes back up, what it will do is rewind the file back to the previous offset, so that the duplicate tuples, when they're written, get written to the same areas of the file. So your file then will not contain duplicates, because the duplicate will simply be overwriting the previous copy. So that's an example of how the output operator needs to be written in order to make sure that you get the effect of exactly once. So our database operator is written that way. The Kafka output operator is written that way. Several of the operators are written that way. But if you write your own, that's something that you need to pay attention to. Okay, so these are screenshots from our monitoring console. It shows you the logical DAG, which is the way the programmer designed the application. And this is the physical view. The second view is the physical view, which shows you the effect of partitioning. There's also visualization that's possible. Various widgets are available, graphs, charts, histograms, and so forth, for visualizing the data coming out of the operators. We have, as I mentioned, a visual application builder, again as part of our commercial offering, that allows you to drag and drop operators and connect them up directly on the screen. Okay, App Hub is the set of app templates that I mentioned before. It's available both as part of RTS as well as on our website. Okay, GE is a customer using Apex in a big way. They have their IoT platform called Predix. And at the core of it, the stream processing engine is Apex. And there's several presentations and recordings of meetups where the GE use case is discussed in more detail. Capital One is also a customer of ours, and they're doing fraud detection. based on Apex processing of input transactions. They have very tight latency requirements, and Apex was able to meet those requirements. Here's some links for the GE use case. And finally, some resources. A good starting point is the apex.apache.org website. There's many, many more links over there. You can subscribe to various mailing lists and other forums. You can download a sandbox. We have a sandbox on our website. The sandbox contains everything installed that you need to develop Apex applications. And a variety of other resources are available on this slide. We're also hiring, so feel free to send your resume over to jobs@datatorrent.com if you find this area interesting and exciting. Okay, that concludes the presentation for today, and I'm happy to take any final questions that you might have. I'm going to wait a minute or two more to see if additional questions appear before I end the session. Feel free to type your questions into the questions panel. All right, it looks like there's no additional questions. So I'm going to end the session. Thank you all very much for attending today's session. Goodbye.